Hi guys, this is Dr. Aeronautics, and at this time, if you haven't watched it already, I suggest you watch the video that I posted after this one, right after this one. It does that every time, and it gets really annoying. So, anyway, basically, as I told you, I was able to go to the Rock On workshop at NASA Wallops Flight Facility, and it was just a huge opportunity, and I'm so glad that I was able to go. So basically, what I did is I went in and built a payload to measure stuff, and then we sent it on a Terrier-Improved Orion to, let me get the official number. Here's the post-launch data. We sent it to 387,111.767 feet, or 73.316 miles, or 118.06 kilometers. So we did break the 100-kilometer international definition of space, but not the spacecraft 120-kilometer definition of space. It took 173 seconds to get to apogee, and in addition to flying payloads, in addition to flying payloads, we were also allowed to fly a very small object on board the rocket. And so I chose to fly one of the Legos that I used to play with as a kid. It's a gold tablet, and I would send my Lego man, but I enjoyed playing with them so much as a kid that I'm not willing to risk it being lost. The only time I would ever send my Lego figure would be on a manned mission, because you know as heck they're going to bring it back. So this is the before picture, and this is the after picture, still largely unchanged, although I don't recall seeing that blemish earlier, so I should perhaps look into that. It might be a reflection, though, because the lighting is a little bit different. But there you go. This little object has been to 387,111 feet, or 118 kilometers, in short, to space. Now, it was not exposed in any way to the vacuum of space, other than the gamma rays, which of course sear through the craft. But there's not that many, so nothing really gets altered. The pressure is held, and the temperature only went up to about 125 degrees Fahrenheit, or about 55 degrees Celsius. So, not very interesting. However, okay, I need to change the shortcuts on these darn things, and now I can't get to it. Apologies. Okay, so I pressed the button on the frickin' Bandicam because nothing else was working. So, I was saying, however, after the flight, they took off the skin of the rocket, and holding the skin were these bolts. And they said, "Come get your space bolts." And when I received 3, I was so excited I nearly blacked out. These bolts were exposed to the full vacuum of space on the outside of the skin, were exposed to 2,900 miles per hour, or about 1,300 meters per second, and exposed all the way up to 118 kilometers in altitude in space, and then landed in the Atlantic Ocean, and they were actually still dripping wet with ocean water, which was amazing. So the other thing, too, was we received these things about 4.5 hours after the flight ended. So everything was still, it still felt alien, which was really neat. Another really cool thing is that in the rocket processing facility, they didn't stop you from getting near everything. So right after lunch, we went back into the building. The door came up, and then this truck starts driving in, and everyone is just like in awe of what they're seeing, because on the bed of the truck, there's no warning. No one's like, get back, get back. All of a sudden the door just opens, and then this truck starts driving in, and it has on it the rocket that went to space. So you can see no one's talking. I assume everyone is in awe. But that was very fantastic seeing that. Another interesting thing was that we were all allowed to sign our names and fly them in space. So here's a grouping of signed names that flew through space. Mine is on here somewhere, but I think it's on the back side. So we were able to get this, and you can see the scratches and everything, and I can actually compare it with an earlier version so that you can see what space does to a steel skin. So this is a picture of what the steel skin looked like before flight. Very red and very shiny, without any scratches or blemishes. I believe this is actually the first flight of this rocket skin, which was really neat because we could see just what one trip through space could do to painted stainless steel. And so these are the rocket technicians that are working on building the actual rocket. Like I was saying earlier, we were actually allowed to get incredibly close. Basically, there were three rules. One, get out of the way of the crane because no one will tell you to. Two, don't get close enough to the technicians that they accidentally walk back onto you. And three, don't touch the rocket because you'll induce a static charge into it. But other than that, there were basically no restrictions. You could go right up to it, take pictures of it, sign it like we all did, and even like mess with your payload while it's still on the edge, which is really cool. So we built this thing at the workshop, and it is basically a G-force activated logging system with sensors all over it. Like I said, there was a Geiger counter, and then there's pressure and temperature data and accelerometers and gyros and a whole bunch of other things on it. The payload was a success, and I actually have the results. That was the main goal of this episode, is to show you the results, so I can show you those. By the way, one thing I wanted to mention is that we were in their testing facility, and I took a picture of their acoustic vibrator. In short, for anybody who does music, this is a giant loudspeaker. If you think that all those loudspeakers you have on your desk or in your car, you think those are loud, you think you have a what do they call those things? Like a wub cannon that just vibrates the entire room and the neighbor's house. This drum, to give you a sense of scale, is 5 feet in diameter. And that is an entire diaphragm that moves back and forth. And here is its amplifier. I did the math, and I believe this is 67,000 watts of sound energy. So you would not want to be standing anywhere near it because it would probably put you into cardiac arrest. Another amazing thing, here is our rocket on its launch pad right here. And another amazing thing was they let us get really, really close to the rocket, like 20 feet close. So this is a picture of it the day before launch, and it's just kind of sitting on here. It has its special engines on. Here at the top we have, oh yeah, you're going to get a kick out of this. I actually have a picture of this. The nose cone has a nose cone. This is the nose cone, and this technician had to screw a nose cone onto the nose cone in order for it to be ready for flight. So, if I wait for that to go away, we have the tip of the nose cone, the RockSat C workshop payloads, the Rock-On payloads where mine is, and the parachute and recovery module, and then the Stage 2 Orion engine and the Stage 1 Terrier engine. So this is the complete rocket ready for flight. So now this is where we're going to spend the bulk of the time. This is where I'm going to explain all of the data that we took. There were some good points and some bad points. Basically what I did was I took my knowledge from spaceflight and school and career, and especially Orbiter, a lot that I know from Orbiter, and produced all 14 graphs, a version of the 14 graphs that I thought the data should look like. And so what I did was I compared what I thought it should look like with what actually appears. So the major stages that I needed to include for all of this was ignition at 0 seconds, the Terrier burnout at 5.2 seconds, the Orion ignition at 15 seconds, the Orion burnout at 40 seconds, 300,000 feet or leaving the atmosphere going up at 98 seconds, payload separation at 125 seconds, apogee at 174, 300,000 feet coming down at 251, the chute deploying at 475, and splashdown in the ocean at 850 seconds. So I had to use all of those to determine that. And so what we find is that this is a graph of time versus samples. So we have, this is in milliseconds, so we have about 1,600 seconds of data, which if I do some quick math, that's like 12 minutes. No, it's more than that. Okay, whatever. It's at least over 12 minutes. Okay, here's an easy way. So 18 would be... Oh, wow. 30 minutes. So we have almost a half an hour of data. We're only concerned with the first million milliseconds, though, because splashdown is at 902 seconds. So we're really only concerned with everything from 900,000 on down. And we took this many data samples during that time. So this is the first thing that we have. This is the low G plus or minus 3G accelerometer in the X direction. And this is, I think, I had to build all of this data from the hex values that came back. But I believe this would be considered level 4 data. That's the number of times that I've had to apply some sort of function or program to it before I could actually get the legitimate values in G-force equivalents. So we can see what happens here is the system is overwhelmed for the first 40 seconds as the engines are firing. The Orion shuts off and we coast at 0G in free fall. And then at 120,000 seconds, we get this impulse here. That's payload separation. And then this continues up until about 300,000 seconds. And at 250,000 seconds, we go through 300,000 feet. So basically what happens is we go through re-entry. Everything goes crazy. The thing gets jittered around between 2.5 and 0 Gs. And then it finally stabilizes out, and then right here, this pinch here, is where the parachute deploys. It falls all the way down to splashdown at about 700, oh sorry, I got the time wrong, not 850 seconds. 729 seconds of splashdown. So here we can see the response here, and then suddenly it just drops in, and then we can actually see the wave patterns here in the ocean. It landed 42 miles or 96 kilometers off of the coast of North America in the North Atlantic Ocean. This was our only bad sensor. This is the acceleration in Y, which never quite reaches 1G and starts at 0. So there, I could probably recover this data by applying some sort of mathematical formula to it. Most likely a negative 1 over r squared kind of thing. But I'm not that interested in recovering this data because it would take too long and I have a redundant sensor. So here's the acceleration low z. And this is, oh yeah, by the way, as you're looking at the rocket, x would be, if you're looking at the disk like a coin, x would be one direction of the coin in the plane of the coin, y would be another direction of the plane of the coin, and then z direction is looking towards the nose cone and the engine. So z is up, down. So what we have here is, again, for the first 40 seconds, the accelerometer is overwhelmed. It can't cope with the g-forces, and it finally stabilizes at 1g here. And it stabilizes at 1g because we have... actually, I don't think I've translated this graph right. It's probably 0g's. But basically what happens is the rocket spins up to about 6 hertz or 6 spins per second, which is very fast. And that can induce your accelerometers. So those, like the Y one, for instance, well, it was messed up, but you'll see the medium Y looks better. So then we have payload separation here, re-entry, and deploy parachute here. So you can see this will fluctuate because the parachute was deployed. And the parachute gets deployed out of the bottom. That's why the G-forces go down and not up. And then we have a parachute full, and then you have splashdown here, and then you're under 1G of acceleration normal from the Earth. And here are the waveforms right here. Then we have the medium accelerations, so the medium X, again being overwhelmed. Actually, no, not being overwhelmed, because this is the X direction. A little bit of vibration while the engines are going. Then it stabilizes because of space. This says -1 because I think I didn't translate the graph correctly, but I'm not concerned about it. Then we have payload separation, then it goes all crazy during re-entry, parachute deploy, and then splashdown, and then the waves again. Okay, so here's our good Y sensor. And then we have the same basic thing, vibration from the engines. Then we have the payload separation, re-entry right in here, parachute deploy, splashdown, and then the ocean. And this is one of the ones that actually works. But it too gets overwhelmed because I believe the Z goes only to plus or minus 12. So it gets messed up for the first 40 seconds of flight while the engines are fired. Then it goes to 0Gs. This one I believe is correct. So it cruises through space at 0Gs, and then we start re-entering. So there's a huge slowdown here, and then parachute deploys, splashdown, and it stays 0Gs because the way it splashes down is like dropping a boat into water. It doesn't align up down. It aligns along the plane of the water. So if it's not aligned up down, then it won't detect the 1G of acceleration from Earth. Okay, and now we have our real high Z accelerometer. And so now what we get is two graphs, although I think this data is kind of bad as well because there were too many things and probably too much vibration. I believe this is the first stage, the Terrier, goes up to about 13 Gs here, cuts off at 5.2 seconds, and then we have a sample here from the second stage, the Orion, which I think was a little bit cut off. That should be as high or higher. And then we have payload separation, cruise through space at 0Gs, and then re-entry, parachute deploy, splashdown, and then 0Gs because, again, not aligned with the Z-axis. Moving on. Now this one is rather interesting. This is a temperature curve in degrees Celsius, and if I look at this, my guesstimation graph, it actually matches exactly, and I will explain why. I have a good knowledge of this because I work with thermal systems as part of my job, so I'm actually used to temperature curves in space. So basically what happens is it was about 77 degrees on the pad, and of course they would vent it out. 77 degrees Fahrenheit, if you'll give me just a moment, translates to 25 degrees Celsius. And that's about what we have here, 26 degrees Celsius. So then all of a sudden for the first 40 seconds we have a ramp up. This is from two things. The engine firing, actually three things. There being no external connection with the environment, the rocket engine firing and heating up the craft, and friction from the air. And this all stops after about 40 seconds. So what this is now is as the atmosphere starts to drop away, the engine no longer matters because the engine jettisons, and the air friction heating stops because you get out of the atmosphere. But then you have a new problem. When you leave the atmosphere, you can't expel energy to your environment in the form of conduction with the atmosphere. So what happens is you start absorbing the more powerful sun that's unfiltered every wavelength because you're above the atmosphere, and you start absorbing this like a black cloth that can't get rid of the heat. So the sun heats this way up to 120 degrees, and it even starts to go higher. And then what happens is we go through re-entry, so the temperature immediately starts to rise even higher because the nose cone will go up to about 800 degrees Fahrenheit, or about 500, maybe 450 Celsius, before you get conduction with the atmosphere again. When the parachute deploys, you have conduction with the atmosphere, and then the temperature is allowed to fall. And then what we have is splashdown, and you'll notice that this right here is a isochoric, or constant volume temperature curve. And so basically, if you've taken physics 2 or an equivalent, what you'll notice is in an isochoric form, basically what happens is you contact the cool ocean water, and it conducts very quickly out of the metal, and it all flows out quickly like a system, and you basically get this nice cool off curve. But the thermal inertia is huge because the thing is full of pressurized air, so you get that. And speaking of pressurized air, like I said, this is a completely sealed environment to space. What they actually do is they actually pressurize the vessel with nitrogen and check it the night before to make sure that it doesn't leak, and to begin atmospheric stressing so that it gets ready for the vacuum. So they've actually pressurized it to about 1.66 atmospheres. This is already 168 kilopascals of pressure. You'll remember from my orbiter videos that the normal atmospheric pressure is 101 kilopascal. And what happens is, as the craft starts to heat up, you have PV equals NKT. So the temperature goes up, but there's nowhere for the volume to go. So the gas wants to expand, but there's no place to expand, so the pressure starts to rise. And it keeps rising until re-entry, where we can see the same thing, and then that drops off as conduction with the atmosphere occurs, and then finally the parachute deploying, and then splashdown, and then you can notice very quickly this isochoric curve. As condensation occurs, the pressure drops very quickly, and it stabilizes upon touching the ocean. So then we have the gyros, and this measures the rotation of the axis in degrees per second. So gyro X would be the same as the rocket. It would be the same as the rocket. Wouldn't really be rolling, but it's one of the two longer axes of the rocket, basically. And what we have here is a little bit of instability as the engines are fired, and then a constant sort of thing here, and then re-entry goes, and re-entry likes to spin like crazy. You can see up to 150 degrees, 125 degrees per second, and negative 150 degrees per second. So it gets spun considerably fast. In fact, I'd call that a tumble. Because 150 degrees per second means you're lurching from down to up in the matter of a second. So that's a full-on tumble. And then it finally stabilizes when the parachute's deployed, and then you can see here splashdown, all of a sudden 100 degrees per second because it hits the water and then tips over. And then you can see here the waves are torquing it about. And then we have the same thing from the gyro Y, nearly the entire thing. So here it is. I don't need to explain it because it's pretty much the exact same thing. Now gyro Z looks a lot different, and what you'll notice is the values are very high. And the reason why is because they spin the rocket up. So what happens is, as the rocket starts to move faster, the fins on the side force the rocket to start spinning in the Z direction, and this causes stability, believe it or not. It's a gyroscopic law that the faster something rotates about an axis, the harder it is to contort it about the axis. So it's very stable. So what you see here is, as the first engine is fired and the craft starts to move faster and faster, the numbers start to climb. 1,000 degrees per second is approximately 3 revolutions per second. The engine burns out and it goes for 10 seconds. As it coasts, the atmosphere tries to slow it down with friction, so the speed drops off again. Then the second stage fires, and then it starts spinning faster and faster and faster, and it finally peaks off at 2,000 degrees per second, or about 5.5 to 6 revolutions per second, where the atmosphere attempts to slow it down, but then fails because the craft enters space and then holds this stable configuration until re-entry. Re-entry brings the craft down all the way to 0, where it starts to tumble and then stabilize as the parachute is deployed, and then upon splashdown, you can see those are quite large, but the numbers here are much larger, so they're quiet, and this is quiet as well because it's shrunk because of that. And then this one is rather interesting. This is the Geiger counter in millirems per hour. So what you notice here is there's almost a parabolic arc here. If you plot altitude versus time and Geiger counts versus time, you'll notice that they almost perfectly correlate, which is really awesome. So let's go over the special times. We're at about 120,000 feet at 40 seconds, so that's about here. So you start to see a quick rise. We go through 300,000 feet at here, and that's where it goes way up. Apogee is at 174, so apogee is about here, which should be expected. And going down through 300,000 feet is about here, which is where you would expect it. And full-on re-entry and shoot deploy is between 475 and 300. So the shoot deploy is about here, and the re-entry process is here. So you can clearly see, even when it gets down in the ocean, parachute fall, it still gets higher counts because it's still not on the surface, and when it finally gets on the surface of the water, the counts drop. So I thought that was very interesting, and you can really It's an interesting way of taking the atmospheric samples, and you can actually do it as a function of altitude, because I thought I was going to be able to use the pressure function, but I had not known that they were not going to have any atmospheric ports. But the Geiger counter, the gamma rays don't care. They'll go right through the steel craft. So because of that, we're able to see that the counts go up and then down here. And for humidity, you can see here, I don't have to explain it, but you might get it if you've done enough space, rocket science and stuff. Otherwise, that's fine. I can explain it to you. But basically what happens is, as the air gets warmer, more and more water starts entering the atmosphere, the pressurized atmosphere inside the vessel as moisture, and this increases and increases, and then what happens is the pressure starts to rise and the temperature starts to rise. The warmer the air is, the more water that the atmosphere can absorb. So what happens is the humidity starts to drop because it starts warming up to about 55 degrees Celsius. So the relative humidity drops off as the temperature gets further above the dew point. And then it basically stabilizes through space at 45, which is actually quite comfortable. And then parachute deploy, so it stay there, and then splash down. And then here's that isochoric curve. The reason this happens so quickly from 45 to 35 is as soon as the steel skin hits the water, it flash gets cold, and what happens is all the moisture in the air condenses on the edge. So basically what the steel skin is acting like is a very quick snap dehumidifier. So all of the water condenses on the skin of the rocket, and the humidity drops and stabilizes. So that is all of the data, and I'm going to peruse a few other things to see if there's anything else, but we're almost finished with this video. So, some interesting things that I noticed NASA did on their things is their warning labels. So, this is a pressure test cell, and they have this dude with a weird, I've never seen this before, oxygen depletion hazard. So that was hilarious to see. They actually have this on that giant acoustic chamber, and I believe that's there because the air vibrates so quickly that you actually can't inhale the air because the pressure from the waves is too fast. And then the other funny thing was that their laser in their test facility says, "Do not stare into laser with remaining eye." So that's a little bit of a warning that says, in case you were stupid enough to stare into it before, don't keep staring into it. Learn from your mistakes. So I thought that was kind of funny. So the last thing I wanted to show you guys was how all of this fit together. And basically we took that thing that we built, and 5 other teams of 3 had stuff that they built. And so what we basically did was we attached them with these lugs, and they basically go straight up and down to create this nice cylindrical portion here. And you can see my little thing that I flew into space went right into this box here, and this is our thing that we built here. So basically they stack these up, and then these go into cans. So you secure them with lids into these cans, and then these cans get stacked into this rocket frame, which you can see here, and then the rocket frame, which is here, gets covered in this skin. They use a crane to lower a skin over it, and then they secure it from both sides. Then they have a pressure O-ring seal on both sides that they connect to the top and the bottom, and then that basically seals it off as a chamber. So that's all I have. I hope you guys enjoyed this video. I enjoyed sending stuff to space and getting it back, especially those bolts that were on the exterior of this thing. I think that was really awesome, that I was able to get so amazing things. I never imagined myself being able to fly stuff in space. So this is practically a dream come true. And stay tuned on my Norston Lantaniso series. Very soon we're going to be building an airship, but I'm collecting so much string for balloons. It's taking forever. And the other thing is... Oh yes, and I have a spider dungeon. It's taking forever even with a spider dungeon, which is incredibly embarrassing. And I also recommend you stay tuned to my orbital tutorials, because we're going to be doing some more stuff with the Delta Glider 4. So, this is Dr. Aeronautics, and I will see you guys next time.